We will begin to solve illustrative problems to understand the first two stages where reinforced concrete beam undergoes before it will reach its ultimate strength. So here is the problem. Reinforced concrete beam section is 350 mm wide and 600 mm deep. It is reinforced with 520 mm diameter reinforcing bars. The centroid position 75 mm from the bottom of the section. Consider FC prime is equal to 28 megapascal. If the modulus of rupture is equal to 0.62 square root of FC prime, determine the cracking moment of the section in kilonewton meter. Number 2, if the reinforced concrete weighs 24 kilonewton per cubic meter, calculate the uniform load in addition to the beam weight, which will cause the section to begin to crack if they are used for 8 meters simple span. Give your answer in kilonewton per meter. Number 3, if the modular ratio n is equal to 9, calculate the moment of inertia in millimeter raised to 4 of the fully cracked transformed section. Number 4, if the stress for concrete will be limited to 12 megapascal and the stress in the steel is not to exceed 150 megapascal, determine the moment capacity in kilonewton meter of the section. Number 5, calculate the maximum uniform load in addition to the beam weight in the 8 meter simple span without exceeding the allowable stresses for concrete and steel. Answer will be in kilonewton meter. For problem number 1, if modulus of rupture is 0.62 square root of FC prime, determine the cracking moment of the section in kilonewton meter. Since the cracking moment of the section is unknown in problem number 1, we are on the first stage where reinforced concrete beam will undergo before it will reach its ultimate strength. We call this stage the uncracked concrete stage. That is the stage where tensile stresses are less than the modulus of rupture, and the entire cross-section of the beam will resist bending in compression on one side, in tension on the other side. So if this is the neutral axis of the beam, all portion of the reinforced concrete above its neutral axis will resist the compression, and on the bottom it will resist the tension. So here is the distribution of stresses in our reinforced concrete at the first stage. It should be understood that the steel can be neglected at this stage, since the concrete alone can carry both tension and compression of the reinforced concrete section. We have to put also in our mind that at this stage, minimal loads are applied on the beam. So to obtain the cracking moment, we will just make use of this formula, Fr multiplied by Ig divided by Y sub T. Fr is the modulus of rupture given on the problem, that is equal to 0.62 square root of Fc prime. And if we try to substitute the value of Fc prime equal to 28 megapascal in our problem, that is equal to 3.28 megapascal for value of Fr. And for Ig, since the concrete alone will resist both compression and tension, we have to make use of the moment of inertia of the entire section, and it can be calculated by the simple formula equal to Bh cubed all over 12. We try to substitute the values of B and H in our equation. This is equal to 350 and 600 mm respectively. Then we can solve for the value of moment of inertia in millimeter raised to 4. And since our section is rectangular, we can easily obtain Y sub T, that is just equal to the distance from the neutral axis up to the most tension fiber. The most tension fiber of the beam is at the bottom portion, since we are assuming that this is a simple span. So Y sub T can be computed equal to 600 divided by 2 or 300 mm, wherein we can now solve for the cracking moment equal to this value. We are dividing it into 10 raised to 6 to convert Newton into kilonewton and mm into meter. So we can have our answer in kilonewton meter, and that is equal to 68.90. We will now proceed solving problem 2. If reinforced concrete weighs 24 kilonewton per cubic meter, calculate the uniform load in addition to the beam weight, which will cause the section to begin to crack if they are used for 8 meters simple span. So the problem asking us to give our answer in kilonewton per meter. So the unit weight of concrete is given on the problem, that is equal to 24 kilonewton per cubic meter. We try to calculate the self-weight of the beam, that is just equal to the cross-sectional area 350 multiplied by 600. Then we will multiply it by the unit weight. We can obtain the weight of the beam in kilonewton per every 1 meter length. We substitute 350 to the width and height to be 600. Then we multiply it by 24 kilonewton per cubic meter, that is the unit weight of concrete. We divide it to 10 raised to 6 to convert mm into meter. So we can have our answer in kilonewton per meter. Since cubic meter into meter square cancels out, what is left is meter in the denominator. So 5.04 kilonewton will be the weight of the beam due to its self-weight every linear meter. It means that if this is 1 meter, the weight of that beam is equal to 5.04 kilonewton. If self-weight alone of 5.0 kilonewton per meter will be acting on the beam, we can easily calculate the maximum moment by using the simple formula for simply supported beam. Maximum moment, if it is subjected by uniformly distributed load, equal to WL square all over 8. Substitute now the values, we can have maximum moment if weight alone is acting on the beam, and that is equal to 40.32 kilonewton meter. And the difference between 68.9, that is the cracking moment, and 40.32, that is the bending moment caused by the self-weight alone, is equal to 28.58 kilonewton meter. This equivalent bending moment will be an additional bending moment that the beam can carry without exceeding the cracking moment of the beam in a span of 8 meters. Then from the simple formula, M max is equal to WL square. If M is given, we can solve for the value of W. That is what we are going to do here. We can solve for the additional weight that the beam can carry by using this simple formula. So we can replace the value of M and L in our equation, and that is equal to 3.57 kilonewton per meter. So in addition to 5.04 kilonewton per meter weight of the beam, uniformly distributed load of 3.57 kilonewton per meter can be still resisted by the beam without exceeding the cracking moment in a span of 8 meters. So if we add 3.57 into 5.04, that is the total weight that the beam can carry. So it is illustrated in this figure. So if we try to solve for the maximum moment of the beam using the simple formula WL square all over 8, that is for simply supported beam under the action of uniformly distributed load in its entire length, so we can calculate for M max, and that is equal to 68.90. It is just equal to the cracking moment of the beam. It simply means that 8.61 kilonewton per meter will be the uniformly distributed load that should be applied on the simple span of 8 meters in order to reach the cracking moment of our reinforced concrete beam. We will now proceed on problem 3. If modular ratio N is equal to 9, calculate the moment of inertia in millimeter raised to 4 of the fully cracked transform section. Since our problem stated about fully cracked transform section, it means that we are at the second stage where a reinforced beam undergoes before it will reach its ultimate strength. At this stage, additional load will be applied on the beam. It will reach the cracking moment, and it will begin to crack at the bottom portion of the reinforced concrete beam. At this stage, the steel will begin to resist the tension forces at the bottom portion of the beam, and the distribution of stresses will be illustrated by this figure. The stresses on the concrete will remain linear, but below the neutral axis, the concrete can no longer resist tensile stresses, and the steel will do its job to resist tension, since the modulus of rupture at this time is exceeded. The second stage is called concrete crack elastic stresses range. So here is our beam under the action of load. The beam will begin to have crack at the bottom portion near the midspan where stress is maximum. Going back now to our problem, since the beam is fully cracked below the neutral axis, we have to replace the value of area of steel to its equivalent NAS, that is, to transform the area of steel to an equivalent concrete area in order to solve for the properties of this fully cracked transformed section. What we did is we make the two materials similar to each other. Let the distance from the location of neutral axis up to the topmost fiber of the beam to be x, so that the distance from the location of the steel area up to the neutral axis will be the depth minus the distance x. The summation of area above the neutral axis is just equal to the summation of areas below the neutral axis. That is to locate the neutral axis from the topmost fiber of the beam. Say the area above the neutral axis is just equal to x multiplied by 350, and the location of centroid is equal to x all over 2. Then the area below the neutral axis is just equal to NAS. So we can calculate the value of AS since the diameter of steel is given, the number of steel is given in our problem. And that is just equal to 5 pieces 20 mm diameter reinforcement. Applying the formula for computing area of circle, that is pi d squared divided by 4, we can be able to solve for the area we multiplied by 5, that is 5 pieces then we multiply it by n, that is 9, we can have this value, that is 14,137.20 millimeter square. And it is located at the distance of d minus x about the neutral axis. Then we will equate those two areas. So 350 multiplied by x is the area above the neutral axis. The moment arm is x all over 2. And the area below is NAS. The moment arm is equal to d minus x. So in this equation, the only unknown is x. We can calculate for the value of x, and that is equal to 169.47 mm. So for d minus x, that is just equal to 525 minus 169.47, that is equal to 355.53 mm. After solving for value of x, we will now calculate the moment of inertia in millimeter raised to 4 of the fully cracked transform section. So since this is a fictitious area, we have to apply the transfer moment of inertia, that is equal to area multiplied by distance squared. And for the rectangular area above the neutral axis, we will just apply the formula for moment of inertia of rectangular section about its base. So that is given by this equation, bh cubed all over 3. So if we replace the values, 350 for b, h is equal to the height, that is equal to 169.47, the value of x in our problem. We raise to 3 divided by 3, then NAS multiplied by d squared. So y here is just equal to distance squared, so that is d minus x in our problem, since that is the distance from neutral axis up to the centroid of NAS. So that is computed there equal to 355.53 mm. So we can have this value of the moment of inertia of our fully cracked transform section. For problem number 4, if the stress for concrete will be limited to 12 megapascal, and if the stress in the steel is not to exceed 150 megapascal, determine the moment capacity in kilonewton meter of the section. So we can calculate the value of bending moment capacity if stresses in both concrete and steel are given by using this simple formula. Flexure stress is just equal to mc all over I, wherein m will be the bending moment and f is the stress. C is the location of neutral axis up to the topmost fiber if that is under compression, and bottommost fiber if that is under tension. And the moment of inertia is the moment of inertia we have just computed before, and that is just equal to this value. So if we replace the value of F into F of concrete and M into M of concrete, I is to be the moment of inertia we have computed there, and C is just equal to X, since the most compressive fiber of the beam is located at X distance from the neutral axis. So that is the value of C in our equation. So we will now compute for the value of bending moment capacity of concrete given the allowable stress of 12 megapascal. We can have this equation. I, the moment of inertia, multiplied by stress in concrete divided by C. So we can have for the value of bending moment on the concrete section if it is limited to 12 megapascal in stress. So we just apply the formula. So we substitute the value of I here, then substitute the value of F in concrete, that is equal to 12 megapascal. Then we divide it by 169.47, that is the value of C, or that is X in our problem. We just divide it by 10 raised to 6 to convert Newton into kilonewton and mm into meter. So we can have the value of moment capacity of concrete if it is limited to 12 megapascal for the stress, and that is just equal to 136.58 kilonewton meter. So for the steel capacity, if stress is limited to 150 megapascal, we can still make use of this formula. So this time we will replace the value of F into Fs divided by N, and for M, that is equal to the moment capacity of steel, and I is still the moment of inertia, and at this time C is equal to D minus X, since the definition of C in this flexure formula is just equal to the distance from the neutral axis up to the most tension fiber or compression fiber. So we are computing for the stress in the steel, so we have to make use of the distance D minus X from the neutral axis, since that is the location of area of steel from the neutral axis. So we can now substitute the values in our equation. So I equal to the value we have obtained, and Fs, that is equal to 150 given on the problem. Then we divide it by 355.53, that is the value of D minus X. We have computed here the value. Then 9 is equal to the modular ratio, so we have to divide Fs into n to compensate in multiplying the area to the modular ratio. Then we divide also by 10 raised to 6 to convert Newton into kilonewton and mm into meter. So we can have the value, the moment capacity of steel given 150 megapascal for the stress on the steel, and that is just equal to 90.42 kilonewton meter. So it means that the capacity of our beam is just equal to 90.42 the capacity of the steel given the 150 megapascal limitation to its stress. If the bending moment applied on the beam will be greater than 90.42 but less than 136.58 kilonewton meter, the concrete can still resist the stress, but the steel stress of 150 megapascal will be exceeded. As a result, the steel will fail. Therefore, moment capacity will be limited to 90.42 kilonewton meter. Then, problem 5, calculate the maximum uniform load in addition to the beam weight in the 8-meter simple span without exceeding the allowable stress of concrete and steel. So, answer in kilonewton per meter. Since from previous calculation, the bending moment if self-weight alone is acting on the beam is equal to 40.32, if we subtract it to 90.42, that is the capacity of the beam of the fully cracked transform section, we can have a difference of moment equal to 50.10 kilonewton meter. So this bending moment will be the additional bending moment the beam can carry before the beam will reach a maximum stress on the steel equal to 150 megapascal, or before the beam will fail. So from the simple formula M is equal to WL square all over 8, we can have the value of W in terms of M. So if we substitute the value of M equal to 50.10 kilonewton meter with a span of 8 meters length of the beam, then we can have the additional uniformly distributed load that the beam can carry. So this is equal to 6.26 kilonewton per meter. If we add the value of W into our weight in concrete, then that is equal to 5.04 plus 6.2625, and that is just equal to 11.30 kilonewton per meter. So the value of the additional weight and the weight of concrete alone is equal to 11.3 kilonewton per meter. If you try to substitute this value into the equation WL square all over 8, that is maximum moment, it is equal to this value 90.42 kilonewton meter. I hope that you have learned a lot from this example. Those who want a copy of this file in PDF, just like and subscribe, comment down your email below, and I will send it to you. Thank you.